Good afternoon, everyone. My name is Zejin Zhang from the University of Hong Kong and the Robotics and Autonomous Driving Lab of Baidu Research. Today, I would like to introduce our recent work about collision avoidance. This work provides a generalized continuous collision detection framework of polynomial trajectory for mobile robots in cluttered environments. This work will be represented as following 4 parts. First of all, it is a background. In the robotics application, the collision avoidance is a significant problem for mobile robots, such as a group of AGVs and quad rotors. The IROS study proposed different collision avoidance strategies. Among above strategies, there is a key problem to be well solved, that is collision detection. A conventional framework of that is discretized. However, this method may miss the collision between the sampled instance. Thus, continuous collision detection is required. After investigation, we find the CCD for mobile robots still has following 3 challenges. First, bounding objects for robots. The simplest way is using a sphere or ellipsoid to cover the mobile robot, since their collision detections are trivial. However, in some cases, the bounding box become a better choice to compactly represent, whereas leading a difficulty about CCD for the bounding box. Secondly, the environment representation is still an open problem, even if we can use the occupancy grid map or the point clouds. This discretized information cannot be used directly in the CCD. Thirdly, it is inevitable to consider robotics constraints in practice. These challenges provide difficulties for the CCD of mobile robots. To this end, we propose a generalized CCD framework for 4-dimensional mobile robots along polynomial trajectories in the cluttered environment, composed of various obstacle models. The entire workflow of the framework is given in this figure. The contributions can be summarized as following 3 points. In the next, I will give more details about our method. The robot model is first defined. The vertex and edge of the robot formulated in equation 1 and equation 2. Then I will introduce how to calculate the collision, which is a key component in our work. We will consider 3 different collision cases in this paper. Then, the collision condition for these 3 cases can be given in this slide. So, based on these 3 basic collision cases about the edge against others, we can extend the collision condition to the edge of robot against a family of obstacle models, such as the sphere, the ellipsoid, the cylinder, and the polyhedral. This model can be extracted from sensor data to envelop the environment obstacles. Next, we consider the mobile robot working along polynomial trajectories. Specifically, the mobile robot translates in the polynomial form denoted by equation 13. Furthermore, we will estimate parameter in the rotation matrix as a set of degree p polynomial equations of time t. This sine and cosine can be represented as a polynomial in equation 14. If we substitute the equations 13 and 14 into aforementioned robot model equations 1 and 2, then we can find that the vertex and edge of the robot could be converted to polynomial equations of time t as equation 15. After that, if we substitute above polynomial equations into collision condition of obstacle models, then these collision conditions can be transformed as a sequence of polynomial inequalities of time t. Furthermore, we can generate the collision intervals of time t after solving these polynomial inequalities by the proposed roots-finding algorithm. In the next slides, we would like to demonstrate some experiment results. In the first experiment, we test the CCD for the quad rotor. As a result, the collision interval between a box-shaped quad rotor along the trajectory T1 against the ellipsoidal obstacle is exactly determined from 0.6959 to 1.6347 as shown in the red curve. Here is the animation of the quad rotor flying along the given trajectory. Then we test the quad rotor along trajectories T1 to T7 against the various cylindrical obstacles. The collision interval are given in Table 1. We can find the collision-free trajectory. In addition, we also test the CCD for quad rotor with different sizes in the same polyhedral environment. With the size decreasing, the quad rotor has more opportunities to pass through the cluttered environment. In the second experiment, we apply our CCD method to detect the collisions for the cable-driven parallel robot. Intuitively speaking, CDPR's potential collision mainly comes from the straight cables, with the environment. We add the cable model as a segment L1 in CDPR diagram. We construct a tree in the environment, which is modeled as a combination of the sphere, cylinder, and a polyhedron. Here is a demo where the end effector follows a trajectory, and our CCD method calculates the collision at 2 separate intervals. In addition, we highlight the cables that occur collisions when collision occurs. In the last experiment, we simulate a navigation system and put our CCD method into the navigation pipeline. Here is an animation about the AGV working in a sparse polygonal obstacle. It should be noted that the trajectory generated by the DWA are the set of arc segments due to dynamic constraints. So in this experiment, it will demonstrate that our CCD framework also works for non-polynomial trajectory in the use of Taylor series. Furthermore, we test the proposed navigation pipeline in an extreme scenario that is a narrow corridor. If using the original DWA, the dialed obstacle will totally block the corridor and there are no paths could be found. But we do not need to do that since our method describes the robots as a 4-dimensional object. Finally, we can see that AGV is able to safely and easily pass through the extreme narrow corridor. Okay, let's conclude our work. In this paper, we propose a generalized framework about CCD. We have tested 3 different mobile robots with IROS constraints in polynomial motions. Thanks for your attention, and you could find more details about our work at this website. Thanks again.